And our next one will be about the Artemis Base Camp, resilience engineering to enable lunar surface operations.
I'm Ron Freeman, and the purpose of my talk is really to give some options as to the kind of shielding that we may need for different lunar expeditions and lunar missions, as well as because it's going to be very much a robotic kind between a robotic kind of missions between landers and rovers, and of course the CubeSats. I believe CubeSats, and that's going to be in the lunar orbit. I believe we need to really look at the health monitoring status of the hardware that's going to be involved. So can we go to the next slide? In this slide, basically what we're seeing is the surface, the moon is exposed to a cosmic, and this is something that we've already talked about. Uh, there's a cosmic rays hitting the lunar surface. They produce a dangerous spray of secondary particles. And to carefully monitor and measure this radiation environment, NASA's LRO, Lunar Reconnaissance Orbiter, was launched, and it still remains in orbit today. Next slide. This is a slide of the lunar South Pole, in which we believe that the first mission, basically lander, will be placed here and near the crater for the permanently shadowed regions, where it'll be searching for basically water, looking for different sites. And so we're hoping that there are going to be a CubeSat. I believe it's going to be the lunar flashlight, where it's going to be having different cameras of visible and near infrared imaging spectrometers. And in this case, we're going to be seeing a combination of small dust particles, electrical potentials, plus micrometeorites, which can lead to the lunar surface dust particles being levitated under the action of electrostatic forces. Next slide, please. In this case, what we're looking at the GCRs that's composed of the low flux, high energetic ions, and how it can penetrate the different shielding materials. And it can actually penetrate between 10 to 100 centimeters of the shielding layer. And as it passes through these materials, it produces atomic and nuclear interactions and produces an internal environment comprised of not only primary but secondary radiation. That would be protons, neutrons, and helium ions. Next slide, please. Next slide. So the purpose of this paper is to explore the different options in managing the impact of the GCRs and the ionizing radiation effects, primarily on the hardware launch. And this is going to be well before the crewed missions to the moon. Next slide, please. These are some of the different shielding materials, and so we're looking at that to provide shielding against these particles. Materials with a high atomic number are currently being employed, which makes it difficult and costly for outer space expeditions, since they increase the payload of the spacecraft. And so what we're looking at now is that the light materials are going to be more effective, and we're thinking that's where nanotechnology is going to come into play, where we're going to be looking at how the nanotubes and the carbon nanotubes can actually be intertwined within the fabrics such that it can provide a certain amount of shielding. So if we look at aluminum panels with polyethylene slabs for the crew residence area in the International Space Station, we can see that a shielding of between 20 to 30 grams per square centimeter can actually reduce the GCR about only 25%. But with that same density equivalent, we can see that polyethylene can reduce it to 35%. And this is something that we need to explore a little bit more. Next slide, please. So, So here we are looking at aluminized mylar that can be used for thermal insulation, and also contribute to the that would be good for spacesuits, and it contributes to not only thermal insulation but also to protection from the ionizing radiation. So one of the options is to look at boron nitride nanotubes, which offer similar qualities as carbon nanotubes, plus additional traits, including a high heat resistance together with the ability to block the radiation. Now, one thing what we could do is use, and the composite structures can be of a multi-layer, which will provide a high neutron shielding efficiency. So you can alternate a high density polyethylene hexagonal boron with a low density polyethylene layers. And so it's the boron nitrides that's going to, that has a percentage of transmitted neutrons of only 4.16%. Neutron shielding results from neutron scattering and absorption, so the high density boron nitride has a high thermal conductivity. Next slide, please. So we are looking at basically here an abbreviated form of what we're looking of the ground stations on Earth, uh, and we're looking at a lunar orbit that's in with CubeSats and the LRO, and then of course we're looking at landers and the rovers, and this is basically going to be the communication system uh, 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 infrastructure that we're going to be using, where you're going to be able to relay different instructions or data or measurements and alert the ground station such that they can make the decisions to relay it back to either the CubeSat or to the rover directly or the lander directly, such that specific action can be taken place. Next slide, please. So, and we're looking when we're because a lot of this is going to be with a microelectronic kind of circuits. We have to start looking at the kind of materials that we can actually use, and in that sense, we want to be able to prevent what this new form of pollution that's known as electromagnetic pollution, which causes serious problems like equipment malfunctioning, and it affects the reliability. So what we can use is carbon fiber reinforced plastics, which have been widely used in the space industry and because of its excellent strength to weight ratio and its resistance to corrosion. Of course, they have some problems, especially around the joint area where there is debonding and delamination occurring. And so more development need to be done with this. You will see here two plates, composite plates. And so we have a surface response to excitation method, which is a cheaper alternative to electromechanical impedance approach. And it gives the user the freedom for selecting the sensors. One thing about all of these parts is that there are going to be multiple sensors throughout all of the hardware that is going to wherever it can be accessible, and this is going to be able to alert what variations that are out of range, and that's going to be matched to an artificial intelligence database, which can see whether or not there is a warning signal allowed, and to be able to specifically give a kind of a solution that needs to be communicated, relayed back to the lander or the rover to be able to make the necessary corrections. Next slide, please. Next slide.
Okay, in 1 minute.
Oh, I see. Okay. So let's go to the next one after that. Next slide. So here is one thing what we're looking at is we're basically looking at how we can use a safety instrumented system, and where we can actually not only when that we can prioritize the different kind of scenarios that can take place, but we don't have to look, we can look at it from a multi-state, multifunctional operational state, where some of the components and some of the component interactions can be targeted, can be prioritized as to which ones are more time sensitive and critical, and requires a little bit more attention, repair, and resources targeted for that, so that we can at least have when a system is vulnerable, that the recoverability is not only is it time sensitive, but we can actually use that particular time to make the necessary precautions so that at least we can get it back to a partial kind of recoverability, functional recoverability. And with that, I want to thank you very much.
All right, thank you very much, Ronald. So I see that there are a couple of questions that came through. One is a comment. It says there is a clear knee in the shielding curve at 20 centimeters. So what energy range of neutrons have you considered when testing nanotubes or the shielding efficiency of nanotubes?
Well, we're constantly always looking for we're in research and development right now in terms of how better to improve the efficiency of this. And so there are more options that need to be taking place as to how we can develop different kind of nanotechnology composite materials that can be intertwined within the fabrics or the materials such that we can improve the shielding efficiency.
All right. And are there any current materials that can be produced at scale for BNNT and are mass efficient versus more traditional materials?
Well, um, we see the advantage of the boron nitride kind of and the polyethylene kind of composite multi-layer kinds of ways. I think that's one of the approaches that we can use. We can use an alternating layering of the different kinds of composite materials, and that will provide a better shield rather than have a one layer that's a more monolithic, that's more uniform throughout.
All right. Well, thank you very much. I appreciate you presenting today.
Thank you.